Hello, I've made this power supply for my workshop and I've used this old inverter box and I'll show you how I did it. I've used the LM317 for the 4 amp switching power supply. Right, I'll show you the circuit and the design, and as you can see here I've written 1.2 volts to 24 volts. That's the transformer that I've used inside, and this I've used as the voltage meter to show the voltage. It is adjustable using this knob here. You can adjust the output voltage. However, I have not used current adjustment. I've just fixed the current at 4 amp. Here I've shown you that it's 4 amp charge current, and I've used the former AC voltage output as the current meter that will show the current output to the load. And here I've actually made holes for the output voltage, and here is the negative, the black one, and the positive. The positive is the red one. So we'll go inside and I'll show you how I did it, and how I actually made the current limiting circuit. I had to build this power supply for my testing gear. So this power supply is actually a good power supply. It has been done by a number of people, and the later videos will actually show you its performance. So this is the datasheet for the power supply. Before I talk about my design, as always, I prefer that I share with you this document here. My philosophy is electronic waste, to use electronic waste as much as possible. So and this is the name that I've given my YouTube channel, the electronic waste benefit. So right, safety caution is that well, you must have experience working with electricity, and I expect that you have prior knowledge of electronics. There is enough literature on the net for learning electronics. When you are working, your environment must be kept clean and out of reach of children, and I expect that someone who is at least 10 years and above would do these projects. My intention is that these are for learning. The projects are for learning, although some you can actually do them for commercial benefit. That is, you actually produce products. So you can actually modify, you can actually adapt, you can actually improve these projects. For this particular one, well, the design is not mine. It's actually made by National Semiconductor and many other people who have actually done this project. I'm just sharing this one because I did it, and I did it a bit different from the circuit that is provided. So right, resources required, well, normally electronic components, power supply, and soldering iron. Yes, maybe. Okay. Right, okay, and software. Okay, we are not going to use any software here now. So what I expect from you is you dedicate your time, and you must have patience, passion, dedication. And any feedback, please, you can email me on remiremi@gmail.com. Thank you. Enjoy. These are the suggested circuits that you can build using the LM317. Well, it starts from LM117. There is this linear power supply that they suggested, and then the other linear power supply with an op-amp as a current regulator, and you can actually you can actually adjust the current. And then I was thinking that I could use the op-amp as a current regulator. Then I realized, well, I don't really need the current regulation as such, because normally when you are testing, you either need 1 amp or less, or you need the full power. So that's why I didn't bother to actually build the power supply with the current regulation. I just fixed the current at 4 amp. The other thing is there is this power supply that most people have done on the internet. This uses a PNP transistor, but I didn't have the PNP transistor. This is a switching power supply, and it uses a PNP transistor. You can actually do it if you would wish, but I realized, well, most of my tests, I do not really need anything below 1 volt. Well, rarely. I normally need about from 3 volts to about 24 volts. There are cases where I need 48 volts. Well, that will be a special case that I need 48 volts, but otherwise my normal range is around 3 volts to around 30 volts, so that will suffice. The circuit that I built is this one, and as you notice, I'll actually share with you what I did. You will notice that here I made some interchange the adjusting pin with the Vout pin. I suppose this is an error, but I don't know. Someone would actually maybe try it out as is. I didn't have time to try out as is, and I made some changes also on the adjustable pin here. You will check the 15 kilo ohm resistor is not there anymore. This 100 picofarads capacitor is not there. And this 100 ohm resistor is not there. I took it out, and then this capacitor value is not 0.22 microfarads. It's different, and the values of the resistors, well, they are within the range, but not exactly as is. So I'll share with you that, and as you can see, I made a note here that I actually made some changes here. This is the circuit that I did. Okay, this is the input power supply. I put a fan there. I intended to actually put a temperature sensing circuit here, but well, I realized that, well, maybe it's okay to just power on and then the fan will run. And please caution, when you actually put in a fan, make sure that the output voltage here actually is compatible with the fan that you put in there. So my transformer would output 18 volt VAC, and it will not go beyond the limit of the fan. Right, and also you check the differences with that circuit. This part here is just to show the level, generally the level of the output voltage. I used a tricolor LED, and you will see it on the video how it will behave. I've also used an old inverter enclosure with the meters, as you would see on the videos, and on the ammeter side, it's actually measuring voltage. Well, all meters actually will measure voltage, but this one I had to adjust the meter, the current meter, because it has a 47 kilo ohm and the diode inside. I took out the 47 kilo ohm resistor and I put 10 ohm resistor. You can use any ammeter that you find. Here the voltmeter must be able to handle the full scale deflection to about 40 volts, because you have maybe you need a transformer that actually would give you about 35 volts, which is the maximum voltage for this IC here. So you have your input here, power switch, and then a fuse of 1 amp is enough, because this is just about 4 amp times 2400 watts, so 1 amp is enough. The bridge must be able to handle the 4 amp comfortably, so a 10 amp bridge will be okay. And then you have a filter capacitors there to just stabilize the power. 2200 microfarads is okay. You make them 2 of them if you can. It's okay. Here is any transistor of your choice, but I doubled them so that each will share 2 amp because I have actually fixed the output current to 4 amp, so each must be sharing the 4 amp and having a current of 2 amps. I would have maybe tried a Darlington transistor there. I think a Darlington transistor will do much better than a normal bipolar junction transistor. And here is the feedback control transistor, and it's a PNP transistor. Here is the current regulation transistor. It's a PNP transistor as well, and here is the voltage regulation IC, the LM317T. Right. You notice that I interchanged the adjust pin here and the voltage output pin here. On the circuit suggested by National Semiconductor, these 2 pins are actually on different positions. I think that is an error on the circuit. I still need to confirm that. And then the inductor must also be able to handle 10 amps, and here should be a fast switching diode. I've chosen the UF5404 diode. This is I think a 3 amp diode, and the one that I actually used is a 3DF. I think a 3D1F diode. You can use any diode, but it should be a fast switching diode with the parameters to be able to handle 5 times the output voltage. That is at least 100 volt diode, right? And then here you have your output feedback, and you regulate your voltage using this potentiometer here, right? The RV1. This is the voltage adjusting, the volt adjusting potentiometer. Here, if you use a negative 1,2 volts, you have a 0 volt output here. But I realized I do not really need 0 volt to adjust my voltage to 0. Well, there are very few instances that I need any voltage that is lower than that, so I left it at as is. And the output voltage filter again with the big capacitors, since it is a power supply. And then these 2 diodes, LEDs here, you can use a single tricolor LED. They are just to indicate the level of the output. The lower the output, it goes greener. This is what I used. This is an old inverter box, and the meters I maintained, and the LEDs, this is I changed the LEDs. This is a tricolor LED. The voltmeter I put it as is. It's up to 20, up to 30 volts. It can measure up to 30 volts, so my output is not getting beyond 28 volts actually, so this will be okay. The ammeter, I have used the AC voltage meter that was used for the inverter, and actually adjusted the meter with a 10 ohm, remove the 47 kilo ohm and put a 10 ohm resistor there, so it's now measuring millivolts actually. So but I've written here 2 times the amp because it shows it reads half the actual current. So these output resistors, they are 0.47 ohms. So the 0.47 ohm at 1 amp, it will give you around 0.47 volts. So that is approximately the voltage equal to the one that switches on a transistor. So each resistor will give you around 1 amp. But normally the transistor will start to switch below 0.47 volts. So 2 resistors for an amp will do, plus minus. That's why I had to use 5 resistors there to give me around 4 amp, as you will see on my demonstration video, which is coming later. The resistors are 5 watts, and you can put at least 5 watt to 10 watts will be okay, because they will heat up. If you are going for more current, where you would be able to actually design for 10 amps or so, you can actually add more transistors there and more resistors there, in parallel, or less resistances in parallel, this is the output. Binding posts here, they are here, and the voltmeter is you can see is measuring before the resistors. You can also even put after the resistors, no problem there, okay. This is the inside of the power supply, the lab power supply. Okay, the focus is not that good. Okay, we just adjust the focus. Okay. Okay, right. The focus is now perfect. Okay, the voltage is there. The current meter that I've used, the former AC voltage output meter, and this is the transformer that I've used. Okay, let me just show the specs of the transformer. Okay, 17.5 volts. It's a center tap transformer, 17.5 volts, and I've used 2 transformers. The second one, this small transformer here, I wanted to have a negative 1.2 volts output, but then I realized, well, there are very few instances that I needed any voltage less than 1 volt, so I just maintained that the power supply outputs minimum 1.2 volts. So this transformer here, I have maintained it just for the future use. If I intend to use another voltage output, this is a split 15015 transformer. It's smaller than the main transformer. This transformer is a 200 VA transformer, and as you can see, that's a 200 watt rated 200 watt transformer here. It's marked, it's this one here, the marked one, so that's the transformer that I've used, and it has got only one winding at the secondary, so it's one output, 17.5 volts, center tap at 17017, and here is the big capacitor, output capacitor, because it's a DC power supply. The rectifier is here, okay, and then here the heatsink for the transistors. I've used the 2N3055, and here is the choke output, and here the output resistor for current measurement using this circuit here. That's the transistor for the current limit circuit, okay, the current clamp, okay, and then here is the LM317 IC, Okay, and then right, let me show you. Okay, this is just another capacitor. These two capacitors, this is the output capacitor, and also this is the capacitor at the bridge. This is the capacitor for the output voltage. Okay, the black one there, this one, the black one, including that one too. Okay, right, and then the fan, I've made the fan permanent running. I'll use a temperature sensing circuit, and later on I'll install a temperature circuit sensing. Okay, a temperature sensing circuit, okay, for the fan to start only when the transistors get hot at a certain temperature. Right, okay, the negative voltage supply that I wanted to use, this is the right. Okay, right, now this is the heatsink where the transistors are mounted. Okay, that's the black heatsink. Okay, sitting on wooden plank there for insulation. I'll show you now how the circuit behaves. Okay. Okay. Now the power supply is giving power, and you can see that now I have to adjust the voltage. Yeah, I'm adjusting the voltage. Okay. That's the output, and because it's 17.5 volts. Okay, that's the maximum. Okay, I'll show you the maximum voltage. Okay, this is the meter that I use. Okay, now, okay, right. So about that, and I'll show you. Okay, right. It's measuring the output voltage. Okay, and that's the maximum output voltage it can give me. Okay, normally when you load it, it goes to around 24 volts. Okay, because of that one is just give me 26 because my input voltage is a bit high. I'm using an inverter. Right, okay, that's the voltage. Now okay, I will show you the current limit. Current, it's this can output. Okay, right, I'm going to use this automotive lamp. This is an automotive lamp, and I will just show you the rating of this lamp here. Right, this is a 12 volt, right, 60 to 55 watt automotive lamp. Okay, that's the lamp I'm going to use. Right, at 12 volt, I set the voltage there at 12 volt. 12 volt. And I'm going to power the lamp. Okay, and power the lamp. Okay. Right, you can see the current over there. Yeah, that's the voltage dancing, and that's the lamp on. Okay. On. Right, and then current meter. Right, you see at 220. Okay, there I've written 2 times up, so that's 2 2 amps times 2, that's 4 amp. 2,2 amp. Okay, that's about 4 amp. Alright, that's 12 volt. Alright, 4,1 amp. That's 12 volt. And that's the lamp there. Let's see. Let's make sure to set properly. That's okay. That's the lamp. Okay. That's the current. That's the power. Right. Show me the current. Okay. Just current here to current meter. Okay. It's now meter is now on current. Okay. 20 amp. Okay. 20 amp. 20 amp DC. Okay. That's 20 amp DC. Okay, I need to see the current. Okay. Right, that's current. I need to see the current of that guy. Okay. That's the current there. Okay, let me just put the lamp away. See the current properly. Okay, so that's the current. That's current 4.7. So that's 4.7 amps. Okay, that's 4.7 amps. Right, and another good thing about this, I can actually short. I can short the output here. Okay. I can short the output here and still maintain 4 amp. Okay, I can short here. Okay, that's a short. Okay, 4 amp. Next, it's 0 there. That's the short. Okay, and short. So make it positive here. You can short circuit. Okay. And here I've used a bicolor, a tricolor LED there to just indicate the voltage level, just an indication, a rough indication of the voltage level. If I go down to low, going to green. If I go up, going red, a bit, going down. Okay, right. Okay, alright. Okay, so for the minimum voltage, I'll just show you the minimum voltage. Okay. That's the minimum voltage. Okay, that's our minimum voltage. Okay. Okay. So okay, that's our minimum voltage, 1.5 volts. Okay, 1.5 volts, 1.5 volts. Okay, that's good. Perfect. Right, one other thing is, as you can see here are the current sensing resistors. This was this is 0.47 ohm resistor, and there are put 5 of them to get me a maximum of 4 amp. As you know, this is the transistor. That's a bipolar junction transistor, NPN. You can see it. Okay, it's not visible. Okay, there is a bipolar transistor here for current sensing, and the base voltage must be at least 0.4 to 0.7 volts. So adding a 0.47 resistor will actually add plus minus 1 amp to the output. So it's easier, you just add one resistor if you want at least around 1 amp output current. And the current sensing transistor is wired to another transistor, a bipolar junction transistor, which switches off the power transistor eventually.